We will start with chapter 6, which is the time independent perturbation theory. In perturbation theory, we will discuss two cases. The first case that we are discussing is the time independent perturbation, means the perturbation which is not depending on time. The way we discuss the Schrödinger wave equation, we discuss the time independent Schrödinger wave equation and then the time dependent Schrödinger wave equation. So when it is the perturbation, first we will discuss that perturbation or that disturbance which will not depend on time. What is meant by perturbation? Perturbation is a very small amplitude disturbance. We use this thing in physics a lot. When we want to study a system, we perturb that system a little bit and then we study its response. Let me give you an example of the perturbation. Like, for example, you have studied the simple pendulum. Now in simple pendulum, you have derived the time period, which is 2 pi L over G square root. Now how you derived this equation? There is some approximation involved in this. In most of the physics, you will apply some approximation. So how you derive this thing? Let's say we are having a pendulum and this pendulum is with mass m, so it is having a downward force mg. Now when you give a little bit of oscillation to this one, then this is the angle that it will make. It starts from the base and it reaches the high point, and this is theta. Now this will make some components, and the components are like, now the tension in this string is in this direction and the mass, the tension against is in this direction. So here, when the tension is in this direction, the gravitational force is in this direction, we are neglecting the air friction. So this makes two components. This one will become mg sine of theta, and this one becomes mg cos of theta, means the two components, the horizontal component and the perpendicular component. In this case, the perpendicular is here and this is the horizontal component. Here, this is the vertical component. Now, you will remember that we apply this approximation that sine theta, for theta to be very small, we consider this theta very small. So the amplitude of this oscillation is extremely small. So theta is very small, then sine theta will just go to theta, because sine 0 is 0. And when theta is close to 0, then sine of theta will be equal to almost theta. And after this approximation, we just consider, means how much small this is, because if you look at the pendulum, it is going this way, means it's an arc here, but we consider this arc so small that it almost become a straight line. And due to that approximation, we say that the time period is equal to this. Now if, for example, you give this much large oscillation to this pendulum, then this equation will not work, because this equation we have derived after this approximation. And that's the reason that the perturbation is a very small amplitude disturbance. And whenever we study a system, like even if it's a spring mass system, then you will have to perturb it very less. Otherwise, the equations, you are always using approximations and they will not work. So this is the care we will have to do. Now when you apply perturbation, like perturbation, let's say, let me give you an example. Like you are walking, and all of a sudden, a small stone pebble, or let's say a piece of sand, goes into your shoes. Now, that small piece of sand or a pebble is not that much that you are now not able to walk, but your walking will be disturbed, right? Your walking will be disturbed. It will not be the usual walking. You will be feeling that thing when you are walking. So it will make a slight modification into your walking, and that we call like a perturbation. That it will be very, very close to the normal, and the degree of perturbation or the order of perturbation or disturbance will be very, very small. You remember that we have, now we will apply all these things on quantum mechanics. You remember that we have already solved the time independent Schrödinger wave equation, which is H psi equals E n psi. This we have already done. If I put a subscript in here, then I will put in here as well, and to n E n as well. So when Hamiltonian operates on a wave function, it gives you an eigenvalue En and the wave function. Now, let's say that about the wave function, we know that they are a set of orthonormal bases like psi n, and they are equal to, let me write them, m and n. So they are delta mn. They are orthonormal. Like if m is equal to n, it will be equal to 1. If m is not equal to n, then it will be equal to 0. They are orthogonal as well as they are normalized, means their magnitude is equal to 1, just like unit vectors in the vector space. Now we will consider on this Hamiltonian is our operator, so we will consider the perturbation in the Hamiltonian, that now our Hamiltonian is not a normal one, but it is a perturbed one. So I put on the unperturbed a subscript 0 here, and then this will be giving you En0, and here I will put 0 as well, as these are the unperturbed wave functions. Similarly, psi m0 is equal to psi n0 in this delta mn. So this h0 and psi n0 and En0, they are the unperturbed Hamiltonian wave function and its value, the eigenvalue. And now when a situation that this will become perturbed, then it will be h will be equal to h0, the normal one, plus the perturbed one, which will be h prime. I will write h prime here. H prime means I can write h1, h2, h3, but as we don't have that much perturbation, so I just write it as h1. What about our wave function? Our wave function psi, our wave function psi of n will be equal to the normal wave function, the wave function which is unperturbed, and then the correction term to this one when it will become perturbed. So this is the first order correction to the wave function, means when perturbation, this h prime will act, the wave function will also change, and psi n2 plus and so on. So the wave functions will modify. This is the wave function which is corresponding to the normal, this one into the normal value, while these will be the correction terms which are caused by this much perturbation. Similarly, the energy En will be equal to the normal energy plus En1 plus En2 and plus En. The energy will also get modified, and this is the normal energy, the unperturbed energy, and these are the correction to this energy in the perturbed situation. Now it depends how much is the perturbation. As we go to the higher values, then they are actually becoming small in magnitudes. They are means making your value more correct. So they are the small. They, as you go along, then the values become smaller and smaller. Like for example, the ground state energy, let's say of hydrogen, is 13.59 electron volt. Now this value we usually approximate is 13.6 electron volt. Now it is not ending here, but there are some other numbers behind it. And those numbers are actually, when we need more and more accuracy, we will go to more and more numbers. In order to get these numbers, we will have to go to the higher and higher terms. So these values is not, they are very, very small compared to the whole value. So as you go on for the higher terms, the value becomes small. And this is like if you are having, for example, A is your wave function or a physical quantity, and this is the unperturbed, and then epsilon 1 and A1 plus epsilon 2, A2, and so on. Now this is the perturbed quantity. This as a whole we call correction to this term. Epsilon is very, very small. Epsilon 2 is smaller, means this is a big number. This is a correction to it, a small number. This is further a small number, and so on. So as you go along, it is unlike the usual way. You know, when we go higher in the series, our values becomes bigger and bigger. But here you go higher in the terms, the correction terms becoming less and less in magnitude. So this we call is the perturbation. Now, in order to consider an example of this one, let's say we have already solved the infinite square well problem. An infinite square well problem is that on this side you are having x, and this is the potential. On v is infinite. On this side here it is v of x or v of r. It depends what you consider here on this axis. If you consider r, then this is v of r. This is infinity on the walls, and v is equal to 0 inside. This was the infinite square well situation, and you know what kind of wave function it was giving us. Now, if this is modified, like we modify this one a little bit, and let's say now our wave function, our infinite square well is such that it has a bump here. All rest of the problem is the same, but this small bump here is now making some potential. So the wave functions will disturb. The wave functions means this is a perturbation in the system. And now our calculations will be different. How much means when this is that perturbation, so how much our wave function will modify with this, and how much the energies will modify. And this we study in the perturbation. Or another kind of perturbation, let's say like we raise this whole, like we just raise this potential here. Now what is the situation? The situation is such that now the perturbation means this much magnitude is up there, and v is no non-zero there. This is our axis, and this is our perturbation. Look here. So V is no not equal to 0. We have raised the potential by this value. Along this value, let's say this is V naught value. So we have raised the potential. Now what changes on the wave function and on the energy this change will make? Or we can raise half of it like this. Half of the potential we have raised. And then what effect will occur on the wave functions? What effect will occur on the energy of the system? This we study in the perturbation theory. So after all this brief introduction to the perturbation theory is always having two parts. Like one is the solvable part, the part which we have already solved in the unperturbed state. And the other one is the correction terms. They are the terms which you just add with your actual solution, and then you derive your perturbed solution. So rest of the mathematics, if you are clear about this thing, then rest of the mathematics is clear. And let's say we are now applying this. What will be H psi is equal to E psi? What will be now this equation? Now this H is not the unperturbed. This is now the perturbed one. So I will write all these terms here. And this implies that H plus H prime, and this is equal to all the terms of energy. It will be En0. And let me write the psi as well here. It operates on psi. So psi n0 plus psi n1 plus psi n2 and so on. This is equal to, it will give you the energy terms En0 plus En1 plus En2 and so on. Similarly, here I will have psi n0 plus psi n1 plus psi n2. The plus and dots means that it is continued, but we are just writing only these terms. And then you just do simple multiplication. So I just do first with this one is, it is H here, and H is equal to H0 H prime. So do multiply them. So I have H0 psi n0 plus H0 psi n1 plus H0 psi n2. And there are some other terms as well. I will just write them at the end, plus H prime psi n0 plus H prime psi n1 plus H prime psi n2. And there are some other terms. Is equal to means I multiplied this with these three terms, and then I multiply this with these three terms. And this is equal to En0 psi n0 plus En0 psi n1 plus En0 psi n2 plus the other terms I am writing here, En1 psi n0 plus En2 En1 and psi n1 plus En2 psi n, this is 1, and psi n2 plus En n2 psi n0 plus en2 psi n1 plus en2 psi n2 and so on. So I just multiplied en0 with these three, then en1 with these three, and en2 with these three. And now we will have to just look at the terms here. Look at the first term, h0 psi n0. It is this situation, the unperturbed. This one was the solvable part, right? Or the one we have already solved. If I look here, then this is 0 and 0. So I call this zero order. Like this one is zero order. This is zero order. And here as well. And if I look here, this is h0, but psi n is 1. So this is first order. This is first order. Is there any first order? h0 psi n2, this is second order. This one, h prime psi n0. What about this one? This is also first order, because this is first order due to the reason that h prime is first order perturbation. Like h0 the unperturbed and the first order perturbation and so on. But to differentiate, we have the perturbation very small. There are no further, you can say, correction or addition to this one. So this is first order. This one second order. But look here, if I come here, then this is h0 psi n0. This is first order. This one is second order, because h1 and psi 1, h prime and psi n2. So this will be second order. Psi n1 will not remain psi n1 after operating this one, and that's the reason we will call this as a second order. It's another order. This one, the third order will be. If I come here, then this one is the zeroth order, as I have already said. This is the first order, the second order, because here en is 0, but psi n is second order correction. First order, second order, third order. Then second order, third order, and fourth order, and so on. They will go on.